Hello, this is Philip Myers of PEMI Consulting. Welcome back. This is part 2 of the subscription cost series, the math behind what I call the silent tax on your nest egg. In part 2, we quantify how small recurring payments turn into large future losses. This is a quick recap of part 1. Subscriptions feel small because each payment is small and the pain is spread out. The real damage is not the payment itself, it's the future value you never get to keep. That's why I call it a silent tax on the nest egg. Here's what part 2 will prove. The silent tax is not a metaphor, it is mathematics. One idea explains the entire problem: exponentials. We'll keep this simple and practical. Define exponential growth, derive doubling time, and translate it into dollars. From here on, we leave analogy and work entirely in equations. This is the dangerous connection. Subscriptions are dangerous for the same reason pandemics are dangerous: exponentials. COVID doubles infections. Compounding doubles money. Subscriptions steal the doubling. The rest of this section is just quantifying that statement. We'll define exponential growth, derive doubling time, then show that money compounding is exponential too. Finally, we translate it into real life using the rule of 70 and a household subscription estimate. The math starts here. This is about the definition of exponential growth. dx dt is the rate of change in growth. K is just a constant or scalar. X, or x of t, is the quantity at time t. Solving this equation gives the equation here, where x of t, the quantity at any time t, is equal to the initial quantity times the exponential multiplier. The equation says that growth rate is proportional to the current amount. That single assumption creates exponential behavior. So why do we keep talking about doubling time? Because doubling time is intuitive. People can't feel what constant K means, but they can feel how long it takes for something to double. This shows up in pandemics, in money, in bacterial growth, and even technology scaling like Moore's law. Doubling time isn't a buzzword, it's a measurable consequence of the exponential model. Smaller doubling time means faster growth. Larger doubling time means slower growth. Doubling time exists only because the process is exponential. Here's the derivation in 2 steps. Starting with the exponential solution, we define doubling time by t sub d, by the condition that it's equal to twice the starting amount. Solve that for t sub d, and you get log of 2 divided by k. So if k is larger, t sub d is smaller, meaning you get doubling faster. Here is why this matters. If something doubles every 3 days, the early numbers look small, and people underestimate it. But doubling is deceptive. It hides early and dominates late. Just to feel the scale, after 3 days, you're at 2 times the starting amount. After 15 days, you're only at 32 times the starting amount. So it feels manageable. But here's the punchline. 20 doublings is roughly a million-fold increase. And at 3 days per doubling, that's only 60 days. That's why COVID felt like it went from nothing to out of control in a few months. It wasn't sudden, it was exponential. And money behaves the same way. Compounding is an exponential too. Now we shift to money. Compounding has the exact same structure. The growth depends on what already exists. The equation is exponential growth in disguise. For those interested, at the end, I will show the equivalence of this equation with the exponential. Once we accept compounding is exponential, doubling time for money follows immediately. The formula tells us higher rates collapse doubling time because the bottom gets bigger. See the sampling doubling times for various interest rates. That means the opportunity cost of spending rises sharply as rates rise. To make doubling time usable without a calculator, we use the rule of 70. Doubling time in years is approximately 70 divided by the interest rate in percent. So 7% doubles in about 10 years. 10% doubles in about 7 years. 5% doubles in about 14 years. The rule of 70 works well for moderate interest rates. By cost of money, I mean the effective annual growth rate you're giving up. Call it EAR or EAR. At 6 to 8%, the effective annual return, think opportunity cost of capital, money doubles every 9 to 12 years. Over a working career, that doubling is the engine of long-term wealth. If you have a 4-decade career ahead of you, your nest egg doubles about 4 times, meaning your initial savings will multiply by a factor of 16. If you want a precise definition of EAR and some examples, I have that in the appendix. So the real cost is not the payment, it's the future value you never get to keep. So now we'll quantify. To ground this in reality, let's use a simple household estimate. A professional household can easily spend around $300 per month across software, streaming, storage, news, and other recurring services. That's about $3,600 per year. The exact number varies, but this is a credible, representative case for professionals. Let's separate two different costs people often mix up. Assume $300 per month. That's $3,600 per year for 20 years. Cost one is the obvious cost, that's the cash paid. Cost two is the hidden cost. It's the future value that's forfeited had you let it compound over that time. At 6%, the future value of those annual payments is about $132K. At 8%, it's $165K. Notice those totals include the $72K you paid out. So the silent tax is the extra loss beyond the cash. About $60K at 6%, about $93K at 8%. That gap is the exponential penalty. It's what subscriptions quietly steal from your doubling. That difference is the damage to your nest egg, the compounding you never got. Notice what happens when rates rise. At 6%, the forfeited future value is about $132K. At 8%, it's about $165K. At 10%, it's over $200K. Higher rates shorten doubling times, magnifying the compounding penalty. This is the thesis. Subscriptions are dangerous for the same reason pandemics are dangerous. Exponentials. COVID doubles infections, compounding doubles money, subscriptions steal the doubling. So what did we actually prove? We proved that exponentials dominate long time horizons. We proved that compounding is exponential growth, and we proved that subscriptions interrupt compounding by removing the dollars that would have doubled. That is why subscriptions act like a silent tax on the nest egg. Here's the mental model. Subscriptions steal future value. A small monthly payment turns into a large retirement opportunity cost because of compounding. And the damage gets worse as interest rates rise and the time horizon grows. This is the reframing. A subscription is not a purchase. It's a permanent cash flow claim on your future. It behaves like a liability because it drains the exact dollars that would have compounded. So treat subscriptions like capital decisions, not casual expenses. Here's a simple decision rule you can actually use. Ask, how much per year? How long will I really pay it? And what's my opportunity rate? 6 to 8% as a baseline. Then compare the value you get versus the future value you forfeit. You don't need precision, you need decision clarity. To make this practical, use triage. Keep subscriptions that truly multiply your productivity or are irreplaceable. Replace subscriptions where one-time purchase or an open source tool can do the job. Cut inertia subscriptions and duplicates, and negotiate or annualize wherever possible to reduce the monthly drain. This is why subscription creep happens even to disciplined people. The business model is engineered to feel painless, just $9.99 per month. Auto-renew makes the default keep paying. Bundling and feature gating push you into recurring fees, and the spending becomes invisible across cards and accounts. This is by design, not your weakness. A reasonable objection you might have is, I wouldn't invest every dollar anyway, and that's true, but opportunity cost still exists. Even partial investing creates large future value losses. The goal here is not perfect precision. The goal is to stop underestimating subscriptions by an order of magnitude. In part 3, we'll move from math to defenses. We'll build a subscription firewall, controls that prevent creep. We'll set up an annual subscription audit, and we'll cover consolidation and renegotiating tactics and when to pay monthly versus annually versus never. Now that you understand the mechanism, we can stop the silent tax. This appendix is optional, but with just a small amount of algebra, we can derive exactly why compounding produces exponential growth. If you're satisfied with the main presentation, you can stop here. But if you'd like to see the actual mathematics, how discrete compounding leads to the exponential form, and how the continuous limit emerges, this is where we unpack it. The key point is simple. Compounding is exponential growth, not as a metaphor, not as a buzzword, but as a precise mathematical result. And finally, we'll see why the semi-log plot becomes a natural language for visualizing exponentials. Let me be very clear about rate definitions because confusion here causes most errors. The annual percentage rate, or APR, is the quoted nominal annual rate. By itself, it is not a compounding rate. If compounding occurs m times per year, the rate actually applied each period is the periodic rate. What matters for annual growth is the effective annual rate, or EAR. So we must talk about the cost of money. We mean EAR, not APR. You may also see rates written in a continuously compounded form where 1 plus EAR is equal to the exponential e raised to the rth power. One final point. In this deck, I always means the periodic compounding rate, not APR. Here's a concrete example. Suppose the APR is 8% with monthly compounding, so M is equal to 12. Periodic rate is the rate actually applied each month. T is equal to 0.08 divided by 12, or 0.67% approximately. To find the effective annual rate, we must compound that monthly rate over 12 periods or months. So every month the amount accumulated gets multiplied by the factor in the parenthesis. That gives an EAR of about 8.3%. So an APR of 8% with monthly compounding really means the money grows at 8.3% per year. When people hear exponential, they usually picture a curve, but mathematically, it's simpler than that. Exponential growth just means time appears in the exponent. The growth is multiplicative, not additive. One standard form is v is equal to v0 a to the t, meaning the value grows by a constant factor a for each time unit. An equivalent form is v of t is equal to v0 e to the kt, which uses the natural exponential base e. These are two notations for the same core idea. Growth accelerates with time. Discrete compounding means the value grows by multiplying by the same constant factor 1 plus I each period. If the effective interest rate per period is I, then each step multiplies the balance by 1 plus I. After t periods, that multiplication has happened t times, giving 1 plus I raised to the t power. The resulting future value v of t is then the initial value v0 times the compounding factor. That is exponential growth by definition. It's the form v0 a to the t with the base a equal 1 plus I, so that even before we talk about continuous compounding or calculus, standard compound interest is already exponential. Here we're showing how the standard discrete compounding formula can be rewritten exactly in exponential form. The goal is to demonstrate that this does not assume continuous compounding. It's simply an algebraic identity. Start with a standard discrete compounding equation, the familiar finance and engineering growth model. Recall the exact identity shown here. This is algebra, not approximation. Because exponentials and logs are inverse functions, applying both in sequence simply returns the original value. Use that identity to rewrite the compounding factor from step 1 in exponential form. Nothing has changed. Now apply the log rule. Pull time outside the logarithm, separating time from the growth factor. Next, define k as shown. This is the continuously equivalent rate associated with the discrete rate I. Substitute that definition back to express the growth factor in exponential form. Finally, insert that result into the original equation to obtain the exponential form for v of t. Here's the takeaway. This is an exact rewrite of discrete compounding. Continuous compounding has not been assumed. The exponential structure was already present. Doubling time in discrete compounding means the growth factor equals 2. You can see the left-hand side as the compounding growth factor we described earlier. Solving the equation results in the discrete doubling time equation. In continuous form, doubling means the exponential itself equals 2. Solving gives t equal to the log of 2 divided by k, the continuous doubling time model. Here's the takeaway. The same structure, same logarithm, same doubling behavior, whether it's money, subscriptions, or infections. This appendix exists for one reason, to show that the subscription penalty is mathematically exponential. In both discrete and continuous form, compounding growth or future value, v of t, depends on the starting base, v0. The future value is then v of t is equal to v0 e to the kt power. Subscriptions reduce that base by diverting cash flow away from investing, which means you don't lose just dollars. You lose what those dollars would have become under exponential growth. That's why the compounding penalty grows over time. This is the technical foundation behind the main message. Subscriptions steal doubling. On these plots, the y-axis is a normalized growth where the starting value is equal to 1. On the left, linear scale compresses early growth, so everything looks flat. On the right, the semi-log turns exponentials into straight lines. That's powerful because now the slope is the interest rate. At 12%, you get about 6 doublings, 64 times your starting value, while at 3%, it takes roughly 20 years just to double once. High interest rates reward asset holders and penalize borrowers because the same compounding works in both directions. Thank you.